Okay, so Albert Herzog is going to talk about the constant pressure balloon data.
Hello, everyone, and I would like first to thank Dave for the invitation today, and it's a great honor for me to contribute to this special workshop to Colin Hines. I also apologize for my voice, which is likely the results of Paris weather this year. So I will present you some results obtained with long-duration balloon flights in the stratosphere. And I will focus the talk on gravity wave momentum fluxes and intermittency. So you all know that in the atmosphere, as Colin has underlined before, gravity waves mainly transport energy and momentum from below, from the troposphere up to the middle atmosphere and upper atmosphere. The waves are very important. The gravity waves are very important for the global driving of the broad absent circulations, and their scales are so that they are only marginally resolved by GCM, which are used to predict future climates. So most of the gravity wave activity is parameterized in those GCMs, and we know that there are several limitations in those parameterization, especially for the non-orographic gravity waves, which are generally which are described in a very simplistic way. And for instance, most of the non-orographic gravity wave direct parameterizations are using homogeneous sources, which we know are not very realistic. So we are with those flights, which I will present you just after this one. These slides, we will try to provide some answers or some new knowledge of those gravity waves. So we are working with long-duration stratospheric balloons. Those balloons are closed balloons made of plastic, and once in the stratosphere, they are spherical, and they drift on a constant density surfaces in the atmosphere. They can fly for 2 or 3 months, and one of the great assets of those balloons is that they are advected by the winds, so that they move or they are fixed in the frame of reference, which moves with the wind. So they directly measure the intrinsic frequency. I will speak today of the latest campaign we had, the Concordia campaign, which took place during late 2010 and early 2011. We launched 19 balloons from McMurdo, which is a US Antarctic station in the Ross Ice shelf around here. And the balloons were launched when the stratospheric vortex was present over the stations. And you can see that the balloons mainly circulates around the vortex. The altitude of those flights is 60 HPA, so it's about 19-20 kilometers altitude. And we have in-situ measurements of position of the balloons and pressure. And since the balloon is advected by the winds, simply by finite differences, we can infer the horizontal winds from the balloon displacement. And now we have developed a technique to analyze those time series with wavelet analysis, and we can doing that we can recover the momentum flux associated with gravity waves. During that campaign, we achieved to have a sufficiently high time resolution. So we have one observation every 30 seconds along the balloon trajectory, which gives us access to the whole gravity wave spectrum. And this is a spectrum of kinetic energy for one of those flights as a function of intrinsic frequency here. And you can see that we can resolve the whole gravity wave band between the inertial frequency and the Brand-Weissela frequency. And this is quite a unique asset of these kind of observations. You can also see one thing that is great with those balloons, at least above the polar area or high latitudes, is that there is a gap between the gravity wave band here and the planetary wave band around here, so that we can easily segregate waves as a function of their frequency. We have also high precision of GPS altitude and pressure measurements. And this is also a good thing, since what we measure actually is this term here, which is the Lagrangian pressure disturbance, which is due to the Eulerian disturbance, which we are used to, but plus this term here, which is the balloon displacement, the pressure disturbance due to the balloon displacement on the isopycnic surface. And knowing measuring the pressure with high precision, and also the vertical displacement of the balloon with high precision, we can recover the Eulerian pressure perturbation, which gives us access to various wave parameters, the phase speed, the vertical wavelength, wave number, the horizontal wave number, and so on. So typically, this is the kind of results we can obtain with the balloons. This is a map of absolute momentum flux for the whole campaign. So this is an average from late winter to early summer. Remember that this is the southern hemisphere, and we use a log scale here. And what you see here is the flux in the direction of propagation of the wave. And what the most important feature that you can see here is the wave, the wave activity over the Antarctic Peninsula, which is the most the major hotspot of gravity waves above Antarctica. You can also see some enhancement here along the transantarctic mountains around here. On the other hand, the plateau here on the eastern side of Antarctica is a region which is very void of any gravity wave activity. Also, you can see that above the ocean here, far from any topography, there is some wave activity, less than what's happening over the peninsula, but still much higher than what is happening here over the plateau. I've given you some values to have numbers. The highest momentum flux over the whole campaign here is 160 millipascals, whether here we have only 0.6 millipascals. So there is a great difference in gravity wave activity as a function of where you are above Antarctica. Actually, when we look at this map, we are inclined to think that mountain waves are the most important thing. But what I've plotted on the next slide is a zonal average of those values here. And here is a zonal average of the absolute momentum flux. So the latitude is here. This is the zonal average of the flux. The total flux is in black. And the mountain, so the mountain activity or the mountain contribution is in green here. And I just use a very simplistic criterion for mountain waves. I've associated those areas here and along the coast and the transantarctic mountains to mountain waves. And what's happening above the ocean, I suppose, is due to non-orographic waves. And the non-orographic part here is plotted in orange over there. And what is striking is that even though those waves are not so important on the previous slide here, when you look at the zonal average, are as important as the mountain waves, and even more important. And so the zonal average of the non-orographic waves is definitely needed in a gravity wave general circulation model. We can decompose those flux in the direction of propagation as a function of the zonal and meridional momentum fluxes. And the zonal flux is represented here, meridional here. And you can see the fact that the zonal flux is mainly negative, as expected, whereas there's no such tendency in the meridional flux. Although the the mountain waves here are associated with positive, so northward flux. When zonally average, the zonal flux is so negative, so westward, whereas the meridional flux is almost zero. So as I told you before, we are able to recover for each wave packet the phase speed. And on the left panel here, you can see the momentum flux distribution as a function of the intrinsic phase speed of the waves. Whereas here, you can see the zonal momentum flux as a function of the ground-based phase speed. And so most of the flux is seems to be associated with waves. And once again, I would like to show you that the color scale here is logarithmic. So most of the flux is associated with phase speed smaller than, let's say, 40 meters per second. And the intrinsic phase speed spectrum seems to be bimodal with a mode close to zero phase speed and another mode close here to minus 30 meters per second. On the other hand, the ground-based phase speed is mainly associated with wave close to zero. You can see a hint of intro waves, as Colin called those waves around here. So waves associated with negative momentum flux and still positive ground-based phase speed. This mode here is actually associated with the mountain waves over the peninsula and transfer to close to zero phase speed around here. Here is a distribution of a momentum flux and a kinetic momentum flux on the left panel and kinetic energy here on the right panel as a function of vertical wave number on the x-axis and intrinsic phase speed divided by f, the inertial frequency on the y-axis. What I wanted to stress here is that when you look at kinetic energy, most of the kinetic energy is associated with very low, very long period waves or low frequency, whereas when you look at the momentum flux, the contribution is given by a broader part of the wave field, and in particular those high intrinsic frequency, high period waves. Short period waves are very important to the total momentum fluxes. On the other hand, if you look at the vertical wave number, it looks like in our data sets, most of the flux or the kinetic energy are associated with waves with vertical wavelengths shorter than 10 kilometers around here. Remember that we are in the lower stratosphere. This is another distribution of the momentum fluxes and kinetic energy, this time as a function of the horizontal wave number here and the vertical wave number here. And once again, there is a striking difference between the momentum fluxes and the kinetic energy. You can see that the momentum fluxes are mainly associated with waves with horizontal wavelengths shorter than 500 kilometers. Yes, around here. Whereas the kinetic energy is associated with waves with a much longer wavelength. So looking at the kinetic energy is not enough to give us information for what drive the what is the main driver of the global the general circulations. So to finish the talk, I will. This is the last picture, and this is a PDF of the momentum flux with our observations. So the values are here, and this is the occurrence frequency here, and the mean PDF for the whole campaign is represented here in black. And I remind you that the mean value for the whole campaign is around 9 millipascals, so it's really here. And you can see the big spread of the gravity wave events that we see with our balloons, and we can see events with 10 times or 100 times more momentum fluxes than the mean values. Actually, if you look at the 19th percentile of this distribution, it's 15 millipascals. So really here for the whole campaign, but only the 10th highest event here contributes to 50% of the flux. So 10% of the events explain half of the flux we observed during the campaign. And this is even greater above the peninsula, which is the red PDF here, where those events contribute to 65% of the total flux. And on the other hand, above the ocean, the wave activity seems to be less intermittent, and the highest flux, the highest event contribute only to 35% of the flux, which is still a great value. So my conclusion is here. I think that long-duration balloons flights can provide really a full characterization of gravity waves in the lower stratosphere. We have access to all those parameters. The Antarctic Peninsula is the major gravity wave hotspot in the southern hemisphere high latitudes, yet non-orographic gravity waves are as important when Zonal means are considered. Momentum fluxes are predominantly associated with high-frequency, short horizontal wavelengths, waves, unlike kinetic energy. And our observations tend to show that the gravity wave activity is very intermittent. Thank you.
So questions for Albert? Erdal again. You don't get to ask all the questions, Erdal.
Okay. Are you presenting mean results from September to January, actually?
Yes, this is mean results.
So if you, did you have a chance to look at how the spectrum of gravity waves change over time from September to?
Yes, we can do that. I don't remember for the spectrum, but I can tell you for the PDF. The PDF are varying very significantly from September to January. The intermittency is much higher during winter than during summer.
Yeah, because you're going from equinox to kind of solstice times, and
right.
Intuitively one could expect changes in the gravity wave activity.
Other questions? Valerie.
Hi, my name is Valery Yudin. So basically, you discuss absolute momentum fluxes distribution, that's correct?
Yes.
And you basically contrast them with kinetic energy fluxes to show different distribution of F numbers. What do you think? Is it a good idea to approximate this and make comparison? Because this is absolute momentum fluxes.
Sorry, to approximate with?
Compare with energy spectra, because absolute momentum fluxes doesn't provide you the full story.
Yeah.
So how good with approximation for practical purposes to understand wave distribution and wave propagation if you just discuss absolute momentum fluxes? Kinetic energy is understandable. This is basically scalar distribution of wave energy. But absolute momentum fluxes we cannot use in parameterization, we cannot use in the interpretation of data.
Actually, in our gravity wave parameterization, the flux is input at the bottom, and then we look how the wave propagates in the atmosphere.
No, I understand about momentum fluxes, but I don't understand absolute momentum fluxes, because you have different directions.
Okay, but we have the when I speak of absolute momentum flux, if you think in terms of parameterization, it's for instance the sum of the momentum flux over all the direction in which the waves are propagating. And anyway, with the balloons, we are able also to retrieve the wave fluxes as a function. We can obtain the zonal and meridional momentum flux too.
Okay, thank you.
Yeah.
Anything else? Sharon.
I'm just wondering if you, if since the balloons go with the wind and there's a background wind plus the gravity waves, if you can tell anything about the horizontal wavelength information about the waves, in particular, the difference between those over the peninsula and those over the ocean.
Yeah, we can obtain information on that, but not directly because we only have a temporary information. We only have the intrinsic frequency. If we want to obtain information on the vertical or horizontal wavelengths, we have to use the polarization relations and look how the phase difference between the pressure and zonal or meridional velocity disturbance.
Thank you, Albert, for a great talk. I have one quick question. Is there any potential for you to design new balloons that would go to significantly higher altitudes?
In the mesosphere, right?
Well, how high can you go?
With the technology that we use now, we are really limited to 20, 21 kilometers. There are new technology, we can go up maybe to 30, 35 kilometers. But going higher is still, I don't think we will be able to do that in the coming years.
But even a 35 would be a spectacular next step. Thank you for a very nice talk.